This one is for my electricians, my apprentices. This video is definitely for you. And to everyone who just want to understand this thing that travel throughout our houses, throughout our neighborhood, throughout our lives, throughout our bodies. This is for you, man. This is the beginning stage, man. We're gonna get to the bottom of this. Because what we're gonna do, I'm gonna show you guys that you can create your own power. You do not have to buy power from the government, but we might get shut down seeing stuff like this. But bruh, we can turn your whole house system into solar. Man, we can make your car run off water. But this is for everyone who's trying to become an electrician. This video is for you. Thank you.
Transformers are game changers in the field of electrical energy transmission and distribution. The invention of power transformers towards the end of the 19th century made possible the development of the modern constant voltage AC supply systems, with power stations located many miles away from our homes. This incredible machine operates at hundreds of thousands of volts and can handle millions of watts of electrical load. In this video, we are going to explore the working of this incredible piece of engineering. So without further ado, let's start it. A transformer is used for increasing or decreasing the voltage levels of an AC supply, with a corresponding increase or decrease in current. It is a static machine, which means, unlike an electric motor, which has a stationary part called the stator and a moving part known as the rotor, a transformer does not have any moving parts, except for the OLTC and motor drive unit, which we will discuss later in this video. Due to having no moving parts, transformers do not incur any frictional or windage losses, making them one of the most efficient electrical machines. Before diving into the working of a power transformer, let's first take a look at the fundamentals of a transformer. When we move a magnet near a coil, a voltage is induced in the coil. This occurs due to a change in the number of magnetic field lines passing through the coil, or alternatively, we can say there is a change in magnetic flux linking with the coil. This phenomenon is known as electromagnetic induction. The strength of induced voltage depends upon the number of turns in the coil, the strength of the magnetic field, and how fast we are moving the magnet, or we can say, the rate of change of flux linking with the coil. A change in magnetic flux is absolutely necessary for electromagnetic induction. If we stop moving the magnet, no matter how strong the magnetic field of the magnet is or how many turns are there in the coil, no voltage is induced in the coil. Let's replace this bar magnet with another coil. If we connect this coil to a DC supply, the magnetic field produced by the coil looks very similar to the magnetic field of the bar magnet. As the magnetic flux linking with the first coil is not changing with time, no voltage is induced in the first coil. That's why electromagnetic induction does not work with a DC supply. Now, instead of a DC supply, if we feed an AC supply to this coil, an alternating magnetic field is formed. This varying magnetic field creates a change in the magnetic flux of the first coil, and hence, a voltage is induced in the first coil. This is called mutual induction, and it is the working principle of a transformer. Similar to this setup, a transformer consists of two coils, wrapped around a ferromagnetic core. These coils are made with copper, coated with a thin layer of varnish or insulation. The thickness of this coating depends upon the desired level of insulation required. Varnish coating serves to insulate each turn of the coil, preventing any bypasses and ensuring uninterrupted current flow along the entire length of the coil. When either of the two coils is fed with an AC supply, the alternating magnetic field produced by that coil links with the other coil, inducing a voltage. However, this transfer of electrical energy is very inefficient because only a small part of the magnetic field from the first coil links with the other coil. To improve efficiency, coils are wound around a core made of ferromagnetic materials like iron or steel. The coil connected to the supply is called the primary winding of the transformer, and the coil on the output side, or connected to load, is called the secondary winding. The flux produced by the primary winding, which links with the secondary winding, is called linkage flux, while the flux produced by the primary winding, but not linking with the secondary winding, is called leakage flux. It's important to note that leakage flux does not contribute to the transfer of electrical energy, and therefore should be minimized to improve the efficiency of a transformer. A transformer core acts as a pathway for magnetic flux, providing a low-reluctance path. As a result, most of the magnetic flux produced by the primary coil links with secondary coil, making the transfer of electrical energy more efficient. As the core is also made up of conducting material, the alternating flux passing through the core induces loops of current inside the core due to electromagnetic induction. These loops of electric current are called eddy currents. Eddy currents cause energy loss inside the core in the form of heat, which reduces the efficiency of a transformer. That's why, in a transformer, a laminated core is used instead of a solid ferromagnetic core. A laminated core is made up of thin sheets of iron or steel, each coated with insulation.
Investing in gold and silver is smart. Buying gold or silver with Vaulted is simple.
These sheets are tightly held together to minimize the air gap between them.
My nigga sleep hard.
Your ass.